In this video, I'd like to discuss energy level diagrams and how they relate to chemical reactions. So for chemical reactions, on top of having reversible and irreversible reactions, we also have exergonic and endergonic reactions. We regularly refer to exergonic reactions as spontaneous and endergonic reactions as non-spontaneous. And what's neat is perhaps spontaneous and non-spontaneous really are the best descriptions of exergonic and endergonic reactions, in the sense that they describe what's going on very, very well. So if you recall from previous lectures, we've discussed why anything in the universe happens. So in particular, virtually everything that does happen happens so as to lower overall energy. So what we could say about a reaction that is spontaneous is that we expect it to lower its overall energy. Whereas we might expect a reaction that is non-spontaneous to raise overall energy. In other words, something has to do work on the reaction, something has to add energy in order to get it to go forward. Whereas a spontaneous reaction will happen, as it is named, spontaneously, because the products will be at a lower energy than the reactants. So let's think about an arbitrary chemical reaction that we've talked about before. A plus B goes to C plus D. We can represent exergonic and endergonic in what's called an energy level diagram. So an energy diagram will have two axes. Energy on the vertical axis and time on the horizontal axis, meaning that as we go higher and higher on the diagram, it's representing increasingly high energies. As we go right across the diagram, time is passing by. Now, what we could say initially is that A and B, our two reactants, are going to have some energy. And exactly what that value of energy is a little irrelevant. But some energy on our energy axis is A and B. So if we know that this reaction is spontaneous, then we expect the final products to be at a lower energy than the reactants. In other words, if it happened on its own without anybody doing anything to it, then we expect it to happen because it decreased energy. So in other words, somewhere on here, if we know the reaction is spontaneous, we can predict that C and D are at some lower energy than A and B. Now we want to think about how we can connect these two energies over the passage of time. So it might be your first inclination to just draw a straight line connecting these two energy levels. But in reality, something a little more complicated has to happen. So I want you to think about a baseball bat and a baseball. In order for the baseball bat and the baseball to interact, one of them has to be moving. If they're both completely stationary, then they cannot hit each other, and therefore nothing will happen. But as long as at least the baseball bat or the baseball are moving, in other words, one of them has to have some kinetic energy, then a reaction can happen. But if the baseball bat and the baseball are not moving towards each other and do not collide, there is never an interaction. Well, the same thing could be said of A and B. In order for A and B to interact or react like they do in the chemical reaction, whatever chemical is represented by A must hit whatever chemical is represented by B, and they have to collide. So in other words, there has to be some inherent energy available that allows the collision to occur because things are moving. We call that the activation energy. And because of that, our energy line will not just go straight from A plus B to C plus D, but we know must increase at first to a crest and then can decrease down to C plus D. So in other words, A and B had to be moving, they had to collide, and then the reaction could happen to C plus D. So this is the energy level diagram for just some generic spontaneous reaction. So let's level out or label out some of the important parts of the diagram. So first off, the distance between where you started, or in other words, the energy of your reactants, to the crest of your hill, the maximum amount of activation energy required, that distance in between those two is what we do call the activation energy. Energy that's not consumed or released in the reaction, but must be present in order for the opportunity for the reaction to even occur. So that is activation energy. Whereas the distance between where you started and where you finished at the end is called the change in energy of the reaction. That is energy that must be either absorbed or released over the course of the reaction. And we usually refer to it as delta E. Right? And that delta sign is just a small triangle. It's just uppercase delta, which is a Greek letter, much like lowercase delta was. It's just got a different shape because it's uppercase. So we've got delta E, which is the distance between the beginning and the end, and the activation energy, which is the distance from the beginning to the top. So I'd like you to take a moment and think about a non-spontaneous reaction and what its energy level diagram should look like. And in fact, consider A plus B goes to C plus D in the case that it's a non-spontaneous reaction. See if you can draw the energy level diagram that you would expect to represent this non-spontaneous reaction. I'm going to pause for a few seconds in the video to give you a chance to pause. So since the reaction is non-spontaneous, what we can say off the bat is that we expect that the products will have a higher energy than the reactants. In other words, someone has to put some work into the reaction. Someone has to do something. Maybe you have to heat it up. Maybe you have to put it under pressure. Maybe you need to hit it with light in order to overcome this barrier. So we know that our products are at a higher energy than our reactants. So we should draw C and D over A and B. Now, there will still be some barrier preventing us from going from A plus B to C plus D. We'll still need to move A and B towards each other in order to do the reaction. So just like before, the crest of the hill must go higher than the end. And so we have a very large energy barrier, or a large activation energy, going from A plus B to C plus D. And then this time, our change in energy will be higher at the end than it was in the beginning. As a final question I'd like to pose for you, consider two energy level diagrams. This one and this one. They both represent some arbitrary chemical reaction. Now, one of them is more likely to be irreversible. So looking at the two diagrams, thinking about the definition of irreversible reactions, and thinking about what everything on the diagram actually means, which one of these two diagrams is more likely to represent an irreversible chemical reaction? I'm going to pause for a moment to give you a chance to think. Okay, so I would expect that the second reaction would be irreversible, whereas the first reaction would probably be reversible. Now, I can only say this because I've got two diagrams to compare with each other. Just looking at one single diagram isn't a good way of determining whether you expect that reaction to be reversible or irreversible. But since we've got two diagrams that we're comparing to each other, we can say which one is more likely to be irreversible. So in our second diagram, if we think about going forward from A plus B to C plus D, it's a very, very steep hill. So what we have to think about is in order to go in the reverse, we have to climb back up that hill to get back to the beginning. And so, in other words, this hill is much more difficult to climb than this hill. So we'd expect that this reaction would be irreversible because the barrier for going in the opposite direction is so tremendous. Whereas this reaction is more likely to be reversible because it has a much more manageable barrier going over. In other words, it's very easy to fall in a hole, but it can be very difficult to climb back out of that hole. And the deeper the hole, the harder it is to climb out. And that's the end of this short video.